last time. We talked about the different types of chemical reactions. So does anyone remember? Give me some examples of chemical reactions that we talked about. Double replacement. Replacement, and we had some subcategories for these ones. Does anyone remember any subcategories for double replacement reactions? Precipitation reaction is usually a double replacement. What about one with acids and bases? What was that one? Neutralization was a double replacement, right? Neutralization. What were some other reactions, types of reactions that we talked about? If we have double replacement, we also have single replacement, right? It's usually with ion exchange, where we're cation, anion are switching places, right? And that had to do with what we called the activity of the metal, which one's going to be more reactive or more likely to be reduced. What else did we have? Combustion was, combustion reaction was another type of reaction that we talked about, right? That was organic molecule plus O2 goes to products. And what was the kind of one of the major byproducts of this reaction for combustion type reaction? Not endo, it was exothermic, right? It releases a lot of heat, right? So this was, you usually create a lot of heat with these. These were very exothermic reactions. And then we had a couple other that we talked about. Decomposition reactions. That's when we take a big molecule and it decomposes into two smaller products, right? Decomposition. What else do we have? I don't remember. What's the opposite of decomposition? Synthesis reaction, right? Where we take two smaller molecules and we make a larger molecule. That's a synthesis type reaction. And then there was another one in a double replacement that we looked at too. That was an unstable product, right? And an unstable product reaction, can anyone tell me what that was? Yeah, usually there's a formation of a gas, right? You make a product. That product is actually not stable, like carbonic acid in soda, and it decomposes into water and CO2, for example, right? So those types of things, there's unstable product, usually that results in some sort of gas formation. All right, so those are all the reactions that we were talking about last time. And so we're just taking, this lecture, we're gonna finish that up, we're gonna start talking about what are called redox reactions and what do those mean. We're not gonna go through every single one of the slides. There's a lot of extra information there about biological redox reactions. We're not gonna focus on that, but there's extra information if you want to see it. Because redox reactions are very important for tons of things, and we'll kind of get into that. So any questions about the reactions we talked about last time? And again, a lot of this was just being able to identify, if you look at a reaction, how would you classify this type of reaction, right? That's the only thing I'm really expecting you guys from this. Balancing the chemical reactions, obviously that's important. That doesn't really go away in chemistry, right? That was also part of this lecture. This is kind of finishing up the second part of this lecture. All right. So oxidation reduction reactions, these are called redox reactions. So they have many important applications. So what classifies these reactions is a transfer of electrons from one species to another, and you have a simultaneous process going on here, right? So we have one reactant is oxidized and one is reduced in both of these reactions. And so some of the things that you see redox reactions, does anyone know any common examples of where you see redox reactions? Does anyone have any idea? Maybe from another class or something of that nature. So one common application we know of redox reactions is batteries. So that's how batteries work, right? Redox reactions look at the transfer of electrons, right? So transfer of electrons from one substance to another which means that electrons are moving in this reaction. And so the way batteries work is you have an anode or a cathode, and at one side of the reaction, right, at one side of the circuit, you have a reduction reaction going on at the surface of that electrode, and the other side of the circuit, you have the oxidation reaction going on. So you're donating electrons to your wire or taking electrons from your wire. When you have those happening simultaneously, you get electrical current that flows through the system, right? So batteries is an important application for redox reactions. So pretty much any battery chemist or physicist is studying redox reactions. How can we make these redox systems more efficient? There's also the opposite of batteries, right? So a battery is a redox reaction that happens spontaneously, meaning it happens automatically, right? You put those in the system and you get electrical current that flows through the system. You can have the opposite, where it doesn't happen spontaneously, and you put electrical current into the system and it drives a non-spontaneous reaction to happen. So that's what's called an electrolytic cell. Right? It's the opposite of a battery, right? Instead of using a spontaneous redox reaction to generate electricity, we use electricity to have a non-spontaneous redox reaction happen. And so one of the applications of this, actually, if you guys kind of followed pop culture trends and fads and stuff, has anyone heard of like hydrogenated water? Right, where they have extra hydrogen gas in your water. So one of the common non-spontaneous redox reactions is water splitting. You split it up into oxygen gas and hydrogen gas. And so one of the health fads right now is if you drink water that has a higher concentration of hydrogen for you, then it's better for you. I don't think there's any evidence that supports that, but you can actually see a electrolytic cell when you put water into these water bottles that have this reaction happening. So you turn it on, you see bubbles start forming, and what's happening is you're putting electrical current through a little catalyst at the bottom of your fancy water bottle, and it's causing water molecules, when they come to the surface of your catalyst, they get split into hydrogen gas and oxygen gas, right? So we get something that looks like H2O goes to 2H2 plus O2 gas, right? So it splits the water molecule into its elemental forms. So that's the little bubbles you see in these cells. Obviously, that one isn't very useful for your health, but water splitting is one of the ways that people are trying to look at purification of ocean water, right? If you can split it into its constituent parts and then get it to condense somewhere else, then you can take out all the things that you don't want, right? So you'll have pure water at the end of that. So in an electrolytic cell, you put current through the system, you use energy to then cause a non-spontaneous redox reaction to happen. Why don't we use that for purification of water? Well, it requires a lot of energy to do that, where it's just not that efficient in converting water or salt water into pure drinking water. Right, so it's taken to other chemicals. What's that?
Do you mind if I grab my model some of that?
No. Yeah, so
Sorry about that.
so for electrolytic cells, that's you get the opposite, right? You generate current, or you put current into a non-spontaneous redox process. Professor Niga's actually worked on redox chemistry for his PhD, so if you have more questions, you can ask him about batteries and redox chemistry. So those are two applications of redox reactions, and also in your body, almost all energy you derive from ATP, NADH, if you guys have heard of these things, the Krebs cycle, electron transport chain, right, in biology, those are all redox processes. And you use these gradients of concentrations to get a kind of cascade reaction happening to generate molecules that have energy stored in them. So that's how we get energy in our body too, is also through redox reaction. So redox reactions are extremely important, and we see them everywhere in almost any system that we understand, in any living system, right? Because it's a very good way to generate energy or use energy. And it all has to do with the transfer of electrons, right? And so we've talked about, up to this point, so I'll just put biology, right? Because biology also uses redox chemistry. We've talked about what oxidation and reduction are, right? So redox chemistry is focused on the movement of electrons. Oxidation, right, the acronym to remember it is oil rig. Oxidation is the loss of electrons, and reduction is the gain of electrons, right? So oil rig is how you can remember what's oxidation and what's reduction. And so combination, decomposition, single replacement, combustion reactions are all examples of redox chemistry. And that's mainly because when you look at chemical reactions, you're looking at bonds breaking and forming, and when bonds break and form, usually electrons are moving around as well, right? The bond is the sharing of the electron. So that's how we remember oxidation reduction. And we also have our other ways we can remember oxidation reduction, right? We can think about it in terms of movement of hydrogen, movement of oxygen as well, right? Like oxidation, for example, that's where the name oxidation comes from. If you gain oxygen, that's like losing electrons. Those two things go hand in hand with each other. Reduction is also losing oxygen. It's the same thing. You gain electrons, you lose oxygen. Or hydrogen, if you lose hydrogen, the same thing as oxidation. If you gain hydrogen, it's the same thing as reduction. All right, so we can also think of it as loss of electrons or gain of O, loss of H. So hydrogen and electrons follow the same trend, or we can think of it as loss. Reduction can be thought of as the gain of electrons or loss of oxygen and gain of hydrogen. Right, so both those are other ways we can think about it. So if you forget, okay, I have lost electrons, I don't remember if that's oxidation or reduction, you can also look at the movement of oxygen in that chemical reaction to determine what's going on as well. Okay, any questions on oxidation or reduction? And again, a redox is just where we have both of these things happening simultaneously. One reactant is, or one species is going to be oxidized, and the other one's going to be reduced. And so how we represent a redox reaction, so up here, this is our redox reaction, is we can use what are called the half reactions to then identify or classify the redox reaction, right? So above we have a simple, how would we classify that chemical reaction besides redox? How else could you classify that? If we're talking about single replacement, synthesis, double replacement, double combustion, or any of those things. Yeah, the first reaction. So the first reaction is the overall redox reaction. How else could we classify that reaction? Yeah, that'd be a synthesis, right? We're going from two smaller constituent parts to make one larger molecule. So this would be a redox synthesis reaction. Well, how do we know that it's a redox process? Well, whenever we have an element in its pure form, meaning it's not bonded to anything else, or it's in its natural state, right? So calcium or sulfur, their natural states are just elemental, like it is right there. If we have hydrogen, oxygen, fluorine, or any of the other halogens, those are in their natural form. They're in the diatomic form, right? So these are the natural form for hydrogen, oxygen, fluorine, chlorine, bromine, and iodine. We have them found in their diatomic form. Remember, those are the 7 weird elements, and nitrogen as well, that when they're naturally found, they're always found in their diatomic form. They don't exist in their elemental form. Whenever you have an element that's in its natural form, its charge should be what? What do you guys think? Neutral, right? Because there's nothing bonded to it. It's not sharing any electrons. It's not transferring any electrons yet. So both of these are going to have a neutral charge on them. And what we call these numbers here, because these are called the oxidation numbers. Right, so the oxidation numbers is basically just the oxidation state. The reason we call it numbers is because we're not just going to be looking at ionic compounds, we're also going to look at covalent compounds. And in a covalent compound, it's not the actual charge on the element, it's just the number we use to represent how the electrons are moving away or to or from that element. So those are the oxidation numbers. Once calcium and sulfur bond ionically, what is the charge on calcium in that ionic bond? What's the preferred oxidation state of calcium if we look at the periodic table? Yeah, it's +2, right? This becomes 2+. And what's the charge on sulfur? 2 minus, right? So in our redox processes, even though the molecule is completely neutral, and we need both sides of the reaction in our redox reaction to be the same charge, right? It's overall neutral on the left, and it's overall neutral on the right, because all the charges cancel out with each other. However, we've seen that electrons have moved through this system, right? The calcium started off neutral, and now it has a 2+ charge. So what happened to the calcium? It got oxidized, right? It lost electrons, so now it has a positive charge. And so this is the oxidation half reaction. Right? In the oxidation half reaction, the way we represent that is that we start off with a 0 charge on the calcium, and then we lose 2 electrons. So we draw the electrons on the product side. And what about sulfur? What did sulfur do in that reaction? It gained 2 electrons, right? So that becomes the reduction half reaction. And so the way we can represent our redox process is in terms of the 2 half reactions. One describes what's being oxidized, and one describes what's being reduced. And together, when they happen simultaneously, we have a reduction process. All right, so if you had a system where you had one, cathode or anode, where the oxidation was happening, and at the anode you had the reduction happening, then you would have electrical current because these electrons aren't just traveling to the other element, they're traveling to the current carrying wire, right? And if you get this movement electron, that's what generates electrical current. All right, so what I want you guys to be able to do is then if you look at a simple redox reaction like this, you can determine what's being oxidized and what's being reduced, and then write the half reactions for that. All right, so for example, if we have something a little bit more complicated, here we have a reaction of magnesium metal with hydrochloric acid, which is something that you guys have done in lab, right? You should get something that forms magnesium chloride and hydrogen gas. Originally, the charge on magnesium, what should be the oxidation number for a magnesium metal? Yeah, it should be not +2. It'll be +2 on the product side, but what about on the reactant side? Here, what form is that magnesium in? Okay, it's neutral, right? Yeah, it's in its elemental form, so it's going to be neutral. So initially, it's 0 here. What about the chlorine? Chlorine likes to form what? What charge? Does anyone know? What's the preferred oxidation state for chlorine? It is negative, right? How many electrons does chlorine need to look like a noble gas? 1, right? Which means that it'll be a -1. And so halogens, oxygen, we'll go over some examples, but halogens, they're always -1. Oxygen is always -2, because we're going to be looking at not just ionic compounds, but covalent compounds. That's what the charge or the oxidation number is for those compounds, the same way we think about the oxidation state of oxygen always being -2. And then hydrogen, when it's part of a molecule, does anyone have any idea what hydrogen will be? +1. So hydrogen will be +1. So hydrogen is +1 in this case, and chlorine is -1. And so now we're going to look at the overall movement of electrons onto the product side. And what is the charge of magnesium now on the product side? +2, right? And then because we have 2 chlorines, that's -2 there, right? So now we've made that's neutral. So what happened to magnesium? It was oxidized, right? And what about for hydrogen here? What's the charge or the oxidation number of hydrogen on the right-hand side? 0, right? Because hydrogen is one of those weird elements that's found in its diatomic form. That's its natural state, right? So this is going to be 0, which means that hydrogen started at +1 because that's its preferred state. That's its oxidation number whenever it's part of a molecule that's not hydrogen gas. And it goes to its natural state, which is H2. Right? So hydrogen started at +1 and it went to 0. which means it gained a negative charge. It gained an electron, so it was reduced. Right, so this is the reduction reaction. The way we represent that, again, is for oxidation, electrons are on the product side of that half reaction. And for reduction, electrons are on the reactant side of that reaction. The reason that we have 2 here for these species being oxidized or reduced is because we have 2 hydrochloric acid molecules reacting with a magnesium atom, and we form H2, right? So we go from a charge of +1 to 0, which is what happens to hydrogen each time. We do that twice. And chlorine isn't shown in the redox reaction. Sometimes it can be shown, but it isn't necessarily shown because chlorine isn't oxidized or reduced in this case, right? Chlorine starts off at -1 per chlorine atom, and it ends at -1 per chlorine atom. Right? The transfer of electrons happens from magnesium and hydrogen. And we can also think about our other definition of oxidation and reduction here, where we talked about, well, if you lose hydrogen, right, that's the same thing as losing electrons. That's being reduced, which is what happens to the hydrogen here. And then if you gain hydrogen, or sorry, you lose hydrogen, sorry, you become oxidized. Technically, it was the chlorine that lost the hydrogen, but it's involved in the transfer from electrons to the magnesium. And so one thing to keep in mind, so we're not going to go over balancing full redox reactions because it can be kind of complicated. But in every redox reaction, the total number of electrons in each half reaction has to be the same, right? Because if something's on the opposite side of 2 reactions, you should be able to add both of these reactions together to then get your full, or to regenerate your full redox reaction. And when you add 2 reactions together, reactions together, we can't ever subtract 2 reactions because it doesn't make physical sense. But if something is on the product side of one reaction and the reactant side of the other, that means they cancel out of the total reaction. So things on opposite side of reaction arrows cancel out. So what that means, if we were to add these 2 reactions, this 2 electrons is on the product side of our oxidation half reaction, and these 2 electrons are on the reactant side of our reduction half reaction. So those 2 will cancel out when we add them together, and when you do all that, you should regenerate your original redox reaction. Okay. And so just to give you an idea of what a biological system, the oxidation and reduction can look like, if we look at this next example of methyl alcohol making formaldehyde, in this case, we see that this molecule, which is called methyl alcohol, right, it would be kind of hard to look at the exact change in the charge on the carbon. We can do it. We can do it for our oxidation numbers, but we can also think about it in terms of the loss or gain of hydrogen, right? And originally, our methyl alcohol has 4 hydrogen atoms, and on the product side, we have lost 2 of those hydrogen atoms. So that's the same thing as it being oxidized. And if we were to add up all of these oxidation numbers here, we should see the same trend in looking at the oxidation numbers for each of these atoms in our redox reaction. And so hydrogen, what was the charge associated with hydrogen? +1, right? If it's bonded to a molecule, it's associated with +1. This would be neutral hydrogen on this side. So each one of these hydrogens, that's +1 here, and that's +3 because there's 3 hydrogens right there. They draw the chemical formula for organic compounds a little differently because this is an alcohol, and so the O and the H are bonded to each other. If you guys go farther in chemistry, you'll see plenty of that. But I'm not going to expect you guys to write the oxidation numbers for a covalent redox process like this one. I'm just showing you that the idea of losing hydrogen is the same thing as being oxidized. So the oxygen carries what number? -2, right? So that's the oxidation number for oxygen. And the total charge on methyl alcohol is what? Based off of the chemical reaction that's given to you. Right now it's 2, but the overall charge, right, there's no charge right here, which means that the overall charge is 0, right? It's a neutral molecule, which means that if we have 3 or 4 positive charges and 2 negative charges, or 2 negative oxidation numbers, what does the carbon have to be for the whole molecule to be neutral? Right, we're basically saying that 3 plus 1 minus 2, all this has to equal 0, right? So what else, what charge are we missing here? -2, right? Which means that this carbon has to be -2 in this original molecule, in this methyl alcohol. And so this is actually, this carbon, whenever we're looking at redox processes, usually it's the non-hydrogen, non-oxygen elements that you're looking at the transfer of electrons from. So let's see now if we look at the formaldehyde molecule. So this is what methyl alcohol looks like, just to give you an idea of what these molecules look like. Formaldehyde looks something like this. Double bonded O. And then hydrogen gas is just, those are what those molecules look like. And so if we have 2 hydrogens on the formaldehyde molecule here, what's the total charge associated with that? Each hydrogen should be what? +1, right? Each hydrogen is +1, right? Oxygen is -2. So if there's 2 hydrogens, what should that be? +2, right? It should be +2. And we have 1 oxygen. What's oxygen here? -2, right? And overall, formaldehyde is neutral, right? Because there's no charge written for formaldehyde. That's what tells you that it's going to be a neutral molecule, right? So what does carbon have to be in this case to keep this molecule neutral? 0, right? Which means that carbon goes from -2 to carbon 0, right? Which means we did what? We're going from something that has a lot of negative charge, right, to something with less negative charge, which means we got rid of some electrons off the carbon. Yep, so this would be oxidized, right? And the idea that if we're gaining oxygen, we're losing hydrogen, right? So here we can see immediately that we lost hydrogen, right, because that's one of the byproducts of this reactant. It's harder to see that we gained oxygen, but if we look at these molecules, right, we have an oxygen-carbon bond here. Another way that we can think of gaining oxygen is if we form another carbon-oxygen bond, and that's what happens in formaldehyde, right? We see that now we have a double bond where we start off with a single bond with the oxygen. So that's a way that we've gained oxygen, which is the same thing as oxidation. And then by looking at the oxidation numbers, we see that, well, carbon actually has lost electrons, which is also how we define oxidation. So the half reactions in this process would be a little bit harder to write for covalent molecules because they don't just break up as easily. However, the idea of writing these oxidation numbers works in this case as well. You just treat the covalent molecule as if it was the oxidation state and the oxidation number were the same thing, right? And the ones you don't know, which would be like carbons, nitrogen, sulfur, those are the ones you're not sure about. You have to look at the overall charge on the molecules to determine the movement of electrons. However, you'd be able to look at this too and see, oh, well, I lost hydrogen. That's the same thing as oxidation. That's another way that we define that. Okay, so that's in a biological system. All right, let me see if I want to skip ahead or continue. Are there any questions on that? Okay, so let's see. We're looking at a complicated, unsaturated, it's not that important that we know what unsaturated means here, can be converted into a saturated fatty acid by the reaction shown below. Would we classify this as an oxidation or a reduction reaction, right? This isn't going to be a full redox process. We're only going to have one of the half reactions shown here. What do you guys think based off of the definitions that we just said, right? These are some pretty complicated molecules. They're probably very large molecules, right? 18 carbons, 32 hydrogens, and 2 oxygens. Right, what were the different ways that we could classify reduction, let's remind ourselves, and oxidation? All right, so how do we classify oxidation? Yeah, gain oxygen, loses hydrogen, and then also loses electrons. Reduction was the loss of oxygen, gain of electrons, or gain of hydrogen first, and then gain of electrons. Right, so how would you classify this reaction based off of any of these definitions here? It should be a reduction. Why can you see that immediately?
Because it's gaining the 4 hydrogens.
Yeah, you're gaining 4 hydrogens here, right? This is being added to this molecule to make this new saturated fatty acid, right? So even without knowing anything about the definitions that go into this reaction, we can determine if it's oxidized or reduced just based off of this definition. So this right here shows that this is a gain of hydrogen, which is a reduction process. All right, any questions on that? All right, so here we can think of, I don't know why I went all the way back to there. Change that. We wrote down all of our different definitions of oxidation and reduction, and they all can come into play here. That's why the addition of water is usually considered a neutral process, because losing a water molecule is losing oxygen and losing hydrogen. And those two things usually cancel each other out. All right. So what about these two reactions, right? So this is the reaction of succinic acid, which provides energy for ATP synthesis. And these are things that you'll see if you take any biology class or any biochemistry class. And you usually see the movement of these hydrogens moving around. You're like, well, how is this related to energy? Well, now you know that it's related to redox processes, which are good ways to use or generate energy. So succinic acid, which is this one, is it going to be oxidized or reduced in this reaction? So we're losing hydrogen, right, which is the same thing as losing electrons, and gaining oxygen, right? So this is going to be oxidized, right? We lost H. All right, we start off with 6 hydrogens in this molecule, and we end up with only 4. And we could go through and we could check with the oxidation numbers that this would also be true. We would see that the carbon atom is losing electrons in this process, right? Because 6 hydrogens should have a positive charge of what? Or positive oxidation number of what? All right, hydrogen was what? +1. And oxygen was what? -2. So 6 hydrogen should be what? +6. 4 oxygen should be -8, right? 4 oxygen, 4 times -2. So then for this to be neutral, which it is because there's no charge associated with this, what does carbon have to be? Or what does the 4 carbons have to be? +2, right? Because I'm at +2 + 6 -8. That gives us a total neutral of 0, right? Which means that each carbon has like half a charge on it, right? This is why we call them oxidation numbers and not states, because in a covalent molecule, you're sharing these electrons, so you can have half charges and stuff associated with them. Then in the next, on the product side, if we're looking at the reduced form, or sorry, oxidized form of succinic acid, right? 4 hydrogen should have what? Oxidation number of what? +4. Oxygen should have a total charge of what? -8, because we haven't changed the number of oxygens, which means now the 4 carbons should have a charge of what to make the molecule neutral? +4, right? So carbon goes from +2 to +4, right? So that means that overall these carbon atoms have done what with their electrons? Right, we're starting from a small positive number and we end with a larger positive number. Yeah, we've lost electrons, right? Because as we take more electrons away, the more positive our atom becomes, right? So this is also how we know that it's going to be oxidized. And what about for the next reaction, FAD, right? FAD is a more complicated looking molecule, that's why it's just abbreviated by that. It's reduced, right? Because we've gained, right? Hydrogen is on reactant side. And that means that we've gained H or been reduced. All right, so we can look at the movement of electrons, or we can look at the movement of oxygen and hydrogen to look at what species are being oxidized and what are being reduced. In a redox process, we have both of those things happening simultaneously, and we can write the half reactions that represent each thing happening. Okay, and I wouldn't expect you guys to do the oxidation numbers for reactions like this, mostly for the ionic synthesis reactions. Oops. All right, any questions on that or concerns? All right, so very briefly, I'm going to talk about activity series, right? This is similar to what we talked about last time. We're looking at reduction potentials. Activity series basically determine in this descending order which metallic elements are more reactive than other ones. Hydrogen is also included in the activity series because it behaves similar to metals. And then these are available in textbooks, and these are values that people tabulated. These are actually represented by what are called reduction potentials. Because when we look at activity series to determine if a reaction happens or not, you're usually looking at one species being reduced and one being oxidized, and that's where these values come from, right? They're saying which species is more likely to be reduced in these reactions, right? And the only thing, so I'm not really going to test you guys on this, but the only thing that you need to know, or you might come across in the future, is if you're given a reactivity series and asked to predict if a reaction happens or not. You just have to identify which one's higher on the activity series of the two metals in the reaction, and then determine if it replaces the other metal or not. Right, so for example, if you look at, on the right here, we have what looks like an activity series, right? It actually goes in opposite order of the reduction potential. So in this case, gold would have a higher reduction potential. And so if we look at a reaction of sodium, right? So this is just solid sodium right here, and it gets mixed with magnesium chloride. You say, well, which metal is going to be more active? We look at our activity series, we see that sodium is higher in activity than magnesium, which means that it will take the place of the magnesium, right? So it'll do a single replacement reaction to then make sodium chloride, and it'll displace the magnesium in the ionic compound. And why is that? That's because sodium is more active, which means that it has a smaller reduction potential. Right, so that's how you can predict products for reactions. Whereas if we look at sodium and, well, actually in both of these cases, if we look at sodium and you mix it with silver chloride, you see that the sodium is higher in activity than silver. Where is silver here? Right here, it's much higher in activity, so sodium will also replace the silver in silver chloride with itself, right? So it's another replacement type reaction. In elements that have lower activity or higher reduction potentials, those are not going to be displaced in reaction. So if we look at silver compared to copper chloride, so we mix silver and copper chloride solution, we see that copper is higher on the activity series than silver, which means that it is not going to replace that. So there will be no reaction that happens. If you were to mix these two things in a test tube, what would indicate to you that a reaction is happening? What are things that could indicate that a reaction is happening? If I mix two things together, how would you guys know a reaction is happening? Change of color is one. Precipitation. Temperature change, right? The solution gets hot or cold. And what was the last one that we talked about? Yeah, a formation of a gas, right? Some bubbling, right? So in these reactions, none of these would happen in these reactions because silver is lower in activity than both hydrogen and copper. It means that it's not going to replace anything. There's going to be no byproduct for this reaction, right? So you will not see anything happening. Whereas in this reaction, right, you would see a precipitate forming. You'd see magnesium solid forming if you mixed sodium in a solution of magnesium chloride. In this reaction, you would see silver solid forming, which would turn the solution most likely turn black, or you'd have black specks forming in a solution of sodium chloride afterwards. And this might be a very blue solution that all of a sudden turns clear because salt water is clear, and you'd see black specks forming as a precipitate. Right? So these are how we actually determine whether these reactions, or we can predict whether these reactions happen, because people have spent significant portion of their lives determining the activity series for different metals. Right, so for activity series, the way I'm not going to be really testing you guys on this, but the way that you determine if a reaction happens or not is if it's higher or lower, right? Or if it doesn't happen, you just say that no reaction is going to happen here. So if you mix lead with hydrochloric acid, right, what's going to happen in this reaction? Yep, lead will replace the hydrogen. Why? Because lead is higher in activity than hydrogen, which means it's more likely or more reactive. And it'll probably make a product, and it's probably going to be lead 2 chloride plus hydrogen gas would be a byproduct, right? And lead chloride is probably going to be a solid. You guys wouldn't be able to determine if it's solid or hydrogen gas is happening here, but you would be able to determine that a reaction does proceed in whatever your products were. The reason I know this is because lead usually forms a positive 2 charge, and lead chlorides can be very insoluble in water, so that's why I say it's probably going to be a solid. And then hydrogen in its elemental form is going to form hydrogen gas. So you'd probably get a solid forming here and a gas forming in this solution. right? So that's all I would expect, or this is, you know, to the extent of how you use an activity series. It's relatively straightforward. You just look, is the metal higher or lower in activity, and does the reaction happen or not? Okay, any questions on that? Okay.
I've had a burning question for a while.
Well, let's put that fire out.
When it comes to balancing chemical
Mm-hmm.
equations and everything, so like even with this one, for example, how we have lead plus hydrogen chloride.
Mm-hmm.
So like, how do we at the end of a chemical equation, like let's say initially we have one hydrogen,
Mm-hmm.
in the final balanced chemical equation we have, let's say, two
Mm-hmm.
hydrogen. Where does that second one come from, and does it like get harvested from the atmosphere or
So
something?
it depends on the type of reaction, right? So remember when, what was it, the magnesium oxide reaction that we did where we burned it in the crucible? Right, we started off with just elemental magnesium, and you ended up with a white solid. That white solid took oxygen from the atmosphere to make magnesium oxide. So in that case, you did take it from the atmosphere. You started with magnesium solid plus oxygen gas, and then you made magnesium oxide solid, right? That one we actually did take from the atmosphere. In a situation like this, where you get the extra hydrogen from is because it requires 2 molecules of the acid for the reaction to happen, right? So that's where the stoichiometry comes in, is that you have to combine things in certain ratios so that the numbers add up on both sides of the reaction.
So in that case, would balancing chemical equations just be like hypotheticals? Then like if you wanted a reaction to happen, you would need this amount.
Yeah, it's saying that we'll basically get the ratios to work out. If I know I need 2 hydrogens in the end, that means I need a source that has at least 2 hydrogens, or 2 of the molecules that each have 1 hydrogen for the reaction to proceed. It doesn't tell you about how those things actually break bonds and form bonds, right? Like it could be multiple steps that are actually involved in it. But in the initial reactants and final products, you know that the numbers have to add up to be consistent with each other. So usually, even if you're pulling it in from the atmosphere, like you were with magnesium oxide, you are expressing that in the chemical reaction. There's nothing that kind of, even though it's coming from the outside system, right, it's still expressed in the chemical reaction because you need things to add up on both sides, right? So there's never anything that just spontaneously appears in the chemical reaction. The actual, setup, real life setup of how you get the reaction to happen just has to be able to include an oxygen source in there for that example. And then for the lead chloride here, you would say, well, I need at least 2 times the amount of hydrochloric acid as I do lead atoms. So I need to make sure I at least have enough for that, for the reaction to proceed. Right? Because then otherwise, okay, if you don't have enough hydrochloric acid, that's your limiting reactant, you make half as much lead chloride as you expect for some reason. But you know for this reaction to happen, because of the conservation of mass, that you need the same amount of hydrogens that you started with, you need to end with the same amount of hydrogens, that if I mix these 2 things together, I need 2 times the hydrochloric acid because I need 2 hydrogen atoms from a source, which means that each reaction needs at least 2 hydrogen or hydrochloric acid molecules for the reaction to actually happen. Right? And that's what I mean. The actual process of breaking and forming bonds is probably a lot more complicated than just, lead, HCl, HCl, right? And these kind of just interact with each other and form lead chloride like that, right? Probably what happens is lead comes in, it takes a hydrogen and ionizes that. This goes to something that looks like this, or maybe this has a slightly negative charge that it's not happy with, and then this interacts with another molecule, and it happens sequentially in a number of different steps like that, right? The actual chemical process or the mechanism by what the reaction happens through, you can't understand just from the stoichiometry. You need to do experiments to actually determine how it actually happens. And that's for not, if you're going on in chemistry, that wouldn't be the next semester, that would be the semester after that, where you learn about how you can determine mechanisms from experiments.
Okay.
Mm-hmm.
And one more question.
Mm-hmm.
So let's say we were trying to make a compound or something, rather that be like medicine, anything like that. And let's say, using this example, let's say we just needed chlorine by itself.
Mm-hmm.
We don't have like a pure form of
Mm-hmm.
let's say it's attached to something.
Mm-hmm.
We're trying to make a compound, like a newer compound entirely. Would there be a way to harvest that, like that chlorine by itself? So like, let's say we had dirt or whatever.
Mm-hmm.
We wanted
bunch of others, carpins or something like that, right? Yeah.
Like, how can we, is there a way that we can actually harvest that to the point where it separates the carbon from the
Mm-hmm.
nitrogen, and then we can attach that nitrogen to something else?
Yeah, so that's it. But the thing is, you have to understand the chemistry of decomposing that, right? So that's where you get synthesis, and then decomposition is two opposite things. And so that's actually a popular field of making medicine. It's called natural product chemistry. And it's easier to start from a complicated molecule and reduce that molecule to something that you're interested in than it is to build something up from scratch to something complicated. So you would have to understand the chemistry of how do I break down this molecule to just get what I'm interested in. So if, let's say, you want to pull out all the nitrogen, right? That's what plants do, right? That's what, if you have certain nitrogen fixing plants for soil, if you guys have seen it, like nitrogen fixing, like 4-leaf clovers and stuff like that are really good to have in your garden because they fixate nitrogen, which is important for the, metabolism of the plants that you're interested in. It fixates nitrogen in the soil. But you have to understand the chemistry of how to break down those molecules, right? There's not a one-way method to do that. Just as much study goes into how does these decomposition reactions happen as they do for the synthesis reactions. So, for example, one of the big challenges of designing the nuclear bomb, for example, wasn't the physics, understanding how to blow up or to separate protons and neutrons from each other, or to cause a chain fission reaction. The challenge for building a nuclear bomb was actually the separation of a single isotope of uranium from the other isotopes you don't want, right? So that's what was the bottleneck and still is the bottleneck. Like, how can we enrich? That's what people say, enriching of uranium. That's what they're talking about. How do I separate the isotope that I want from the ones that I don't want? And so that's oftentimes the bottleneck for things, right? You can write an equation, oh, this is how we release all this energy, but actually getting the material sometimes isn't so easy. But yeah, and that's actually what a lot of machine learning algorithms are trying to do, is if you start off with some sort of, right, so there's a lot of traditional medicines and stuff that they work because they are the same molecules that people synthesize in the lab. And so there's a lot of, machine learning, and not just machines, but also people that work on, from this starting point, can I get to other molecules that I want? And that's easier than starting from scratch and doing that. And that's natural product synthesis. But yeah, good questions. Those are things that people think a lot about and very deeply about. All right, any other questions? All right, so that's where we'll leave the chemical reaction.